So, morning. In continuation of previous video, there we discuss a NAND gate decoder, that is max term generator, and how do we use the NAND gate decoder to implement the max term expression by using output AND gate or NAND gate. Also, how do we implement using means min term expression using output AND gate or a NAND gate. Now we see decoder with enable input. So far we discussed AND gate decoder and NAND gate decoder. There we are not considered the enable input. That means decoder have one or more additional input lines. They are referred as a enable inputs. They are referred as a enable inputs. So here we use E for AND gate realization and E bar for NAND gate realization. That means AND gate realization we use active high enable input, and for NAND gate realization we use active low enable inputs. And here the truth table is compressed. The truth table is compressed. That means to say all input combinations are not explicitly appeared in the truth table. So in the compressed truth table, X indicates don't care. X indicates don't care. So in this compressed truth table, several rows of normal truth table are replaced by a single row in a compressed truth tables. Okay. So remember, decoders have additional inputs, that is enable input. Now we'll see AND gate realization of 2 to 4 decoder. I mean 2 inputs, 4 outputs with the enable input. So since it is AND gate realization, we use E as an enable input. When E is equal to 1 means decoder is enabled. When E is equal to 0 means decoder is disabled. So the corresponding block diagram. See, observe the input side 0, 1 and enable En. So to this we connected X0, X1 and E. E is the active high enable input, and the output same 0 to 3, and they are connected to Z0 to Z3. So let's see the corresponding truth table. In the truth table we include enable inputs. Say this is the truth table. In the input side observe E, X1, X0, and outputs Z0, Z1, Z2, Z3. Observe the first row, that is E is equal to 0, X1, X0 is don't care. That means E is equal to 0 means disabled, decoder is disabled. So whatever may be X1, X0, outputs are all 0, active I outputs. So active I outputs 0 means not selected, no one is selected. And similarly observe the next 4 rows, E is 1, E is 1. So that means decoder is enabled. So in the second row, X1, X0 is 0, 0. So Z0 is selected, 1, and remaining all zeros. And for the next row, 0, 1, X1 is 0, X0 is 1. So Z1 is selected, remaining all are 0. This is what the truth table. So here we included enable inputs. Let's see the circuit diagram. Here we included E. So if you write the expression for Z0, observe the Z0 column. If you write the product term, we consider output 1. So output is 1 for the corresponding input combination. E is equal to 1, X1 0, X0 0. So the expression is E X1 bar, X0 bar. See the circuit diagram. We use 4 AND gates. For Z0 AND gate, we connected the input E X1 bar, X0 bar. So Z0 is equal to E X1 bar, X0 bar. Similarly for Z1, observe the truth table. Z1 column, output is 1. For the input combination, E is equal to 1, X1 is 0, X0 is 1. So E X1 bar, X0 is the expression. Similarly, we write expression for Z2 and Z3. So this is the circuit diagram for 2 to 4 and 2 to 4 decoder with active high enable input. Yeah. Now we'll see NAND gate realization of 2 to 4 decoder. Again using enable input. So here we use active low enable. That means E bar. So when E bar is equal to 0, decoder is enabled. When it is 1, decoder is disabled. When E bar is equal to 1, decoder is disabled. So see the corresponding block diagram. Right. So in the input side 0, 1, En, they are connected to X0, X1 and E bar. So that bubble indicates active low input. Bubble indicates active low input. And outputs are also active low. No? So observe output side 0, 1, 2, 3. Output bubbles are connected. And they are connected to Z0 dash 1, Z1 dash, Z2 dash and Z3 dash. So again in the truth table, let's see the truth table. So input side E bar X1 X0. Suppose if E bar is 1, that means decoder is disabled. So whatever may be X1 and X0, all outputs are 1 1. All outputs are 1 1 means not selected, since active low outputs. So in the next 4 rows E bar is 0, that means decoder is enabled. So based on the values of X1 and X0, it select the corresponding output. So if X1 X0 is 0 0, Z0 dash is 0, remaining all 1. If it is 0 1, Z1 dash is 0, remaining all 1 1. So let's see the circuit diagram. In the circuit diagram, so E bar is complemented and it becomes E, and that is connected. Okay. And the remaining same X1 bar, X0 bar plus Z0. So because of NAND gate, in the previous we use AND gate, here we use NAND gate. Because of NAND gate, output complemented. If you write apply the De Morgan law, it becomes E bar plus X1 plus X0. Similarly, Z1 dash expression and Z2, Z3 dash. So if you compare NAND gate realization, we use here a NAND gate, and our enable input is complemented. So apart from this, decoder with enable input is also referred as demultiplexer. That means here enable input is behaves as a data input, and input to the decoder behaves as a select input. Apart from this, the additional feature is it is used to construct a large decoders from the small decoders. So let's see one example. How do we construct larger decoders from a small decoder with the facilities of enable input. Construct 4 to 16 decoder using 2 to 4 decoder. That means 4 input to 16 output using 2 input to 4 output. So the truth table for 4 is to 16 means 4 inputs. Let's say 4 input x3, x2, x1, x0, and 16 outputs z0, z1 up to z15. Here see truth table is splitted. So in the input side, the two variables x3, x2 are named as selector inputs, and the remaining two inputs x1, x0 are named as a decoder input. The output side, again, it is divided into 4 sections, that is decoder 1, decoder 2, decoder 3 and 4. So outputs Z0, Z1, Z2, Z3 are the outputs from decoder 1, and Z4 to Z7 are outputs from the decoder 2. Similarly, Z8 to Z11 are output from decoder 3, and Z12 to Z15 are decoder output from 4. And observe first four rows. Okay, here it is x3 and x2 is 0 0, right? And decoder 1 is selected. Based on x1 and x0 corresponding either z1, z2, z3 are selected, and the remaining z4 to z15 are all 0. That means whenever decoder 1 is selected, the remaining 3 decoders should be disabled. Okay, so decoder 1 has to be selected when x3 and x2 is 0 0. Similarly, observe next 4 rows. x3, x2 is 0 1, and here decoder 2 is selected. Decoder 2 is selected. Again based on x1 and x0, either z4, z5, z6, z7 are 1. The remaining are 0. So that means when the and observe the outputs of decoder 1, decoder 3 and decoder 4 are all zeros. That means whenever decoder 2 is selected, decoder 1, decoder 3 and decoder 4 must be disabled. When x3 and x2 is 0, 1. Similarly, when x3 and x2 is 1, 0, decoder 3 is selected and remaining are not selected. Similarly, when x3, x2 is 1, 1, decoder 4 is selected, remaining are not selected. So, we need 4 decoders, and to select one among the 4 decoders, additional one more decoder. So, we need totally 5 decoders. Let's see the construction diagram. See, one decoder which select one among the 4 decoders. So inputs are x2 and x3, and it is always enabled. If it is 0, 0, 0 output is selected and 0 output is connected to first decoder, so that is enabled. The remaining are 0. The remaining outputs are correspondingly connected to the remaining decoder, so the remaining decoders are not selected. Similarly, when x2 and x3 is 0, 1, one output is 1, the remaining are 0. So correspondingly, second decoder is selected, the remaining are not selected. Clear now? So this is how we construct 4:16 decoder using 2 to 4 decoder. We have industrial decoders that we'll discuss in the next video.